Here we go. So we're in chapter 2 today. We've finished up with stuff that's going to be on the exam. We're going to talk today about conformations of molecules and mostly steric factors, which are all related to the fact that portions of molecules are surrounded by electron density, and that electron density repels the electron density in other portions of the molecule. And so there are this has an effect on the shapes that molecules adopt. I don't know that we'll talk too much about these first two examples because you will have seen them in your undergraduate course, and you will have had a chance, hopefully by now, to spend some time in Gaussian messing around with some of these conformations. A couple of terms that may be useful to you, I think, like I said, maybe most of you know this by now. When we talk about conformations, a very important thing is a dihedral angle. This has a technical definition. A dihedral angle is the angle between two vectors. You can also define it as the angle between two planes, but by a vector I mean you put a point here and a point there and then draw a line through it, and then you do the same thing there. And mathematically, if you've got those coordinates, you can determine the angle. And this describes rotation around a carbon-carbon bond. There is a sign convention for which way is positive and which way is negative, because the angle between two vectors is related to the dot product, which is related to cosine theta. So there is a direction to it. I have never memorized that. Convention, and I don't expect you to. In fact, what we do, as you've seen in Gaussian, is if we want to know a dihedral angle, we simply click on the four atoms and it tells us what it is. So nobody measures these things by hand anymore. All right. And of course, the dihedral angle, in order for it to make sense, you have to specify which two bonds you're talking about. So presumably, they've said, okay, we're going to think about this hydrogen and that hydrogen and what's the angle between them. And notice that at angles 60, 180, and 300, we're at minima, and that corresponds to staggered conformations, whereas if we're at 0, 120, or 240, we're at maxima. And your text shows, and probably in your calculations, what you did was calculate the energy of an eclipse conformation. To do this, you had to tell it to optimize to a transition state. We'll talk more about that later. That's actually an interesting computational problem, because for something to be a transition state, it's got to be almost exactly like a minimum force. If you move any of the atoms, there has to, let's see. A transition state is referred to as a stationary point. That means if you move in any of the atoms in any direction, it wants to go back to what it was, except for the direction that corresponds to the reaction. So in this case, that's rotation around the carbon-carbon bond. Here's butane. What do we need to say about that? You've got two different staggered conformations and two different eclipse conformations. Having methyl groups eclipsed is worse than having methyl eclipsed with a hydrogen. And gauche methyl groups, where the dihedral angle is 60 degrees, is worse than having the methyl groups anti to each other. Okay, anything we need to review there? I know I haven't gone through that in a lot of detail. Okay, sort of boring. Couple other terms that you may encounter just for sort of dihedral angles. Basically, there's a 50-50 line. If you're on this side of it, you can call the group syn to each other, and if you're on this side, you can call them anti. If you're sort of within plus or minus 30 degrees of vertical, you can call that periplanar. That means occupying sort of the same plane. This is why you'll hear, if you're teaching 351 this semester, about how the E2 reaction involves anti-periplanar arrangement of beta proton with its leaving group, and that's the combination of those two terms. I honestly don't really bother with what clinol means, and apparently this is the convention sign. So clockwise is negative and counterclockwise is positive, I guess, for dihedral angles. Okay. And your book will give you some useful increments. It's good to know that each eclipsed carbon-hydrogen interaction is worth about a kcal per mole. And yeah, I think having alkyl groups gauche to each other is also worth about a kcal per mole. One thing your text points out is that gauche is not always bad. So there's this weird molecule, and physical organic chemistry can sometimes devolve into let's make weird molecules as weird as possible and see what their properties are. So this is an example of that. It's 2,3-dimethylbutane or something like that. And it turns out that having the methyl groups you might expect that this would be the best conformation, because at least, though you do have methyl gauche to methyl, at least you have methyl anti to methyl as well. However, what they found is the presence of these two methyl groups on the same carbon, they will tend to distort their bonding so as to be far apart, and when they do that, that causes them to get closer, at least in terms of dihedral angle, to the other methyl groups. This is sort of gee whiz, because I can't think of anything I'd ask you about this other than, oh, look at that. It's kind of weird. But your text says that if you arrange it this way, even though they're all gauche to each other, when they distort their bonding in order to get away from each other, they can do so in ways that don't smash into each other. It can get more complicated, and you've seen this maybe in your computational assignment with pentane. And I totally didn't understand this until actually I sat down and did the assignment myself. So there are just a couple of unique conformations in pentane. They're showing 3 here. There's actually one more that they're not showing you. But for the sake of our discussion, we'll call this 1, 2, 3, 4, and 5. And the two bonds that we're worried about are the bond between 2 and 3, and then the bond between 3 and 4. Now, as we've drawn this, if you were to put your eye in the plane of the page, and I'm a nerd, I can't resist every time I do this. It stopped being funny, but I still do it anyway. We have sort of bloodshot, evil Sith eyes looking down that carbon-carbon bond. You would see that you've got an anti-conformation. Another way to describe that anti-conformation is to say that that dihedral angle is 180 degrees. Another way people will describe this conformation is to give it the letter T, under a lowercase t for trans or anti. We don't typically use trans in a stereochemical sense that way, but you will, when people talk about conformations, you will sometimes see that notation. So we have trans or a 180 dihedral angle here, and then if you were to similarly take your evil Sith eyes and move them to look down the bond between carbon 3 and 4, you would also see a 180 degree bond angle, right? And so you could describe this conformation with 2 dihedral angles. You could call this 180, 180. You could also call this TT, or you could call it the extended conformation or the all anti conformation. But it's those 2 dihedral angles that define what the molecule looks like, or its overall shape.
So TT is just trans-trans?
Yeah. One that isn't shown for you here is gauche trans or trans gauche, they'd be equivalent. That would involve rotating around this bond so that this methyl group was gauche to this group, which they're not showing that for you there. Let's look at this other conformation, and this one's kind of difficult because 1 and 2 are in front and behind each other respectively. We want to look down the bond between 2 and 3. I guess this wasn't ever a methyl group, was it? It was like some R group. We want to look down the bond between 2 and 3, and then the bond between 3 and 4. So if we looked down the bond between 2 and 3, let's see, we would have a hydrogen here, another hydrogen there. It looks like on carbon 1 is a methyl group, so let's put that there. Carbon 3 in the back looks like we have hydrogen, hydrogen, and then the bond between 3 and 4. So that first bond between 2 and 3 has a dihedral angle of 60 degrees. I'm not sure if it's 60 or minus 60. And that won't matter for the most part until we get to the conformation at the bottom. And then let's look down the bond between 3 and 4.
You would just call that last one gauche, right?
Yes, this first one, conformation is yeah, gauche. There is a gauche plus and a gauche minus depending on whether you rotate counterclockwise versus clockwise. And we'll look at these two last conformations because they both involve gaucheness, but one of them is different from the other. If we look down the bond between 2 and 3, you know what? Let's not draw this. Let's actually use a program where we can see the model. Is that okay? Maybe you can draw it later. I forgot. So Spartan lets you draw pentane, and then kind of fun, it has conformations. So there is the all trans conformation. We'll call this carbon here, well, we'll call this one 2, 3, and 4. Doesn't matter, we could have gone the other way, it's symmetric. Looking down the bond between 2 and 3, you can see that's a anti or trans conformation. Looking down the bond between 3 and 4, that's also an anti or trans conformation. That's the lowest energy one. We go up to the next one, and I'm going to cheat and forget which one was 1, 2, 3, and 4. Down the bond between 2 and 3. Oops, no. We've rotated that methyl group from being here to here. Sum that up. So that's gauche. And in the back, we're still anti. So that's an example of a GT or TG conformation. One is anti and the other is gauche. One is trans and the other is gauche. This is an example of a gauche conformation. So we're again going to look down the bond between 2 and 3. And let's go ahead and define the sign convention this way. Let's start from if the alkyl group on the front and the alkyl group on the back were eclipsed with each other. Let's say if we have to rotate the group in the front counterclockwise, that's plus. Okay? So this is a gauche plus conformation. Now let's look at, and we're looking at atoms 1, 2, and then in the back is 3, and then this is 4. I'm going to rotate this up so we can look down the bond between 3 and 4. And notice again, if we imagine starting out eclipsed, in which direction would we rotate in order to get to the carbon in the front to get to that gauche conformation? That's also counterclockwise. So that's also gauche positive. Now, so we would call this conformation gauche plus gauche plus. Whoa. Went to sleep. That's not good. And if we want, at this point, we can draw down the bond between 3 and 4. And again, you see that to get if we draw sort of a line from the carbon group in the front to the carbon group in the back, in both cases, the sense of that is counterclockwise. And so these are gauche plus, there's an equivalent gauche minus, but the effect of that, if you look at the molecule, is to sort of keep those methyl groups on the end apart from each other. One's going this way, the other's going that way. You see that? So this is kind of hard to see, and so tell me if you don't see it, and we'll talk about it. Like, what's confusing so far?
I guess, confused about the signs. Like.
Okay. So that's the sign of the dihedral angle will honestly depend on which carbon we're calling carbon 1 and which one we're calling carbon 5.
So the reason it's plus plus though is, can you just explain that one more time? Like how we know on this that plus.
Yeah, maybe instead of saying plus plus, we can say, is it gauche in the same sense or in opposite senses? Is one right-handed gauche versus left-handed gauche? Okay. Because if you look down if you look down a carbon-carbon bond, there's two positions that are gauche, right? One on the left and the other on the right. And if methyl group was here, maybe it's 60, and if methyl group is here, maybe it's minus 60. All right, so I'm not totally sure what the sign convention is, and we can pretend like we know it or pretend that we don't know it. Let's ask ourselves, is the group in the front on the left or on the right of the group in the back? It's on the left. So let's just call that plus. Okay, so that's a gauche plus. If we look down the next bond, we can ask again, is the carbon in the front on the left or the right of the carbon in the back? It's left. So we got two left-handed gauches. And the effect of that is to keep the methyl groups on opposite sides. Now, a question you could ask is, what would happen if you changed one of those from left-handed to right-handed? So your two gauche conformations were now opposite in sense. Let's look at that. We're going to look, here's carbon 1, here's carbon 2. All right, the group in the front is on the left-hand side of the group in the back, so we'll call that plus. That's a left-handed gauche, or a plus gauche. Let's look down the bond between 3 and 4. The carbon in the front is now to the right of carbon in the back. So that's an opposite gauche sense. And if you look closely, you can actually see that's a little bit distorted from a gauche. The dihedral angle isn't exactly 60 degrees. And the reason for that is that when you have opposite-handedness gauche, you end up having the two methyl groups directly sort of smashing into each other. And I think we can look at this in space filling form. You can see that's kind of a problem. Sometimes people call this a syn-pentane interaction, but that's what we've got pictured here. And this is an example of the gauche plus, gauche minus conformation. And I guess we can draw those Newman projections so that your notes will be complete. It looks like down the bond between. Sorry. Looks like we've got carbon 2 here, and then in the back you have the R group. And methyl group in the front is on the left side, so I guess we're calling that gauche plus. And then looking down the bond between 3 and 4, you would have this, and then it looks like a methyl group in the back. Now the alkyl group in the front is on the right hand side, so this is gauche minus. So it's almost like these two conformations are diastereomers of each other. It's almost like you had a molecule that was RR and another that's RS. They're different. They have different properties. You can think of conformations in that way as well. And this is why, by the way, you could ask, why didn't we do the gauche minus conformation? The answer is it looks exactly like this, just opposite-handedness. It's the enantiomer of that conformation. Same chemical physical properties has to be, right? And why didn't we do the gauche minus gauche plus conformation? Same thing. It's the enantiomer of this conformation. So the idea is that when you go beyond butane and you start to have more methyl groups there, you need to think of not only short-range interactions, but also long-range interactions. If we considered each of these bonds individually, we probably wouldn't have detected that caused the methyl groups to smash into each other, right? But in fact, it did. And so as your molecule gets more complicated, you have to start thinking about these other issues. And this is a common enough issue that your text felt like it was useful to call out. Now, this actually gives us a chance to talk a little bit about a concept called pre-organization, because if you look at that gauche plus gauche minus conformation, notice those methyl groups, carbon 1 and 5, are on the same side of the molecule as each other. And so a question you could ask is, well, why don't I just bond them together, right? 1, 2, 3, 4, 5. And so if you take those two and you bond them together, you now have cyclopentane, and you relieve that interaction by just enforcing it. There's angle strain and ring strain present in cyclopentane. But now you could have a gauche plus here and a gauche minus there, and it doesn't matter because these two are connected to each other. And the idea is sometimes in chemistry we can enforce an unfavorable conformation with a cyclic constraint. You use chemistry to pay the energetic cost of having things in a conformation that wouldn't normally happen. All right. Anything else you want to ask about that?